All right, we are going to use this profit maximization problem to illustrate how we use implicit differentiation or the chain rule to find those comparative statics terms. So we have this standard profit maximization problem in a perfectly competitive market. So we have over here P and W and V. These are market parameters. So these are parameters. Okay. And we want to maximize the profit, find the optimal labor level. So we find optimal L star and K star so that this pi over here, so that pi is equal to P, F, L star and K star and minus W L star, so that this one is optimal. So this is the problem we have. And we assume that we have solutions to the first order conditions. So now we start from this pi function. Pi is a function of L and K, and that's equal to P, F, L, K, and minus WL and minus VK. So we take two partial derivatives with respect to L. We're going to have P, and here F is unknown, so we just use F sub L to denote the derivative, and then we have this, and then we set derivative 0. The second one, we have pi k, and that's P, F, K over here, minus V is equal to 0. Okay. So now we assume L star and K star. They are solutions to these two equations, to P, F, L, minus W is equal to 0, and P, F, K, minus V is equal to 0. And what we want to know is this, because now L star and K star, they depend on function parameters P and W and V, and also K too depends on P and W and V, because these are market parameters. So what we want to find these so-called comparative statics terms. So we want to know, for example, how much this equilibrium is going to shift if we have the underlying wage changes. So what is this one over here? For example, we want to find this. Now, because our little f is unknown over here, we cannot solve L star explicitly, then take the derivative. What we can do is to look at where this L star and K star are from. They are solved from these two equations. So this equation over here and this equation over here. And L star and K star, they are hidden over there, and we can use implicit differentiation to find it. So how do we do that? We first realize that FL is really a function of L and K. Since F is a function of L and K, right? So, and similarly, your partial derivative of F with respect to K is really a function of capital L and K. So what we have over here is really this. We have these two equations. We have P times FL, and we have L star and K star. They are solutions, right? And minus W is equal to 0. And also we have P, F, K, and these are functions of L star and K star to begin with. So we have these two is equal to 0. Now what we need to do is we use the chain rule to take the derivative with respect to W for both equations. And how we do that? Let's draw a diagram. FL is a function of L and K, and L is a function of W. Of course, P and V as well, but they are not relevant for the moment. And FK2 is a function of L and K, and both of them are in turn functions of W. So when we take the partial derivative with respect to W, we need to use the chain rule, and we need to follow all the chains we can have. So let's take the derivative of the first equation. P is a constant, and then apply the chain rule. This is what we have. We have partial f L first with respect to L, and then L derivative with respect to W, and plus partial FL respect to K, and then partial K partial W. So that's the derivative of this part, and we have it over here. And then, of course, you multiply it by P, and then derivative of W with respect to W is 1, so you have minus 1 is equal to 0. So we now have finished the first one, and then we look at the second one, very, very similar. And we have partial Fk, derivative respect to L first, and dL dW, and plus partial Fk respect to K. And then we have partial K and partial W. This time V is a constant, so we simply have 0 over here. Now, what we're going to do is to use the matrix notation from linear algebra. So we will see these are unknown, dl, dw, and dl, dk, dw. This is the one we want to find. So what we have over here is this. So we have matrix form, we have P. Now, if you look at this one over here, partial FL with respect to L is simply FLL. So double derivative. So we have FLL over here. The same thing, we have the second one over here is P, but this time now we have FLK. And this corner we have P, FKL, and then we have P, FKK. So we have a 2 by 2 matrix. If you look at this is exactly the Hessian we have. This one over here. And then we have 2 variables. That's first one is partial L, partial W, second one partial K, and partial W. And then we can move 1 to the right-hand side, and that's equal to 1 and 0. So we now have a linear system to solve with the matrix over here. If we are interested to find these 2 terms over here, now we can put a stop back if you want to, but it's not really a big deal. This matrix over here is the coefficient matrix we know, and then these 2 we can find. We can find them using so-called the Kramer's rule. And notice over here, if we want to find dl star dw, we have to also find dk star dw. They just come together. You cannot just find one without the other. Of course, you can now write down the formula using the Kramer's rule. Kramer's rule says that if you want to find the first component, this is what you have. You will put replace the first column by 1, 0, and then copy the second column, and P, F, K, K. And then put the determinant of the coefficient at the bottom, P, F, L, L, and P, F, L, K. And here then P, F, K, L, and P, F, K, K. So that's your solution. And similarly, you can find the second component, K star, respect to W, using the Kramer's rule. And on the top, now because it's the second component, you replace the second column by 1, 0, and this is P, F, L, L, and then this is P, F, K, L. I should not make it so small, but that's okay. And then the same denominator, P, F, L, L, and P, F, L, K, and P, F, K, L, and P, F, K, K. If you want to find the value of these 4 determinants, you can do that easily. And then we have the formula for both comparative statics terms. All right, that's all.